Hello and welcome to episode 38 of the eBPF and Cilium Office Hours live stream, also known as eCHO. So the show notes, like every week, they're available on HackMD. You can find the link in that corner. It's very hard to get the direction right when you're looking at the screen. Without further ado, today we're not going to do headlines today, and we're just going to skip straight into speaking with our guest. We mentioned this tool a week or two ago in the headlines, bpf-curve for code coverage. So let me bring Leo Di Donato into the stream, and welcome to eCHO. Leo, thanks for joining us today.
Thank you for having me, Liz. Hello, everybody. I'm Leo. I guess you understood that.
As always, if you're watching us live, do let us know where you're watching us from. Ask us questions as we're going along. We always love to hear from you and make sure that we're answering your questions as we go. So, as I said, we came across the bpf-curve tool a couple of weeks ago. Sounds like a really interesting topic to understand how we can get code coverage for our BPF programs. So, Leo, tell us a little bit more about why you've built this tool.
Okay, that's a good question. There are various reasons, a few reasons in reality. Basically, something that I always wanted while working in the recent years with BPF was a tool able to give me the possibility to, let's say, visualize the path, the internal path of the BPF programs that I was writing when they would have been running in the Linux kernel, so actually running there in the BPF virtual machine that's in there. Usually I guess like many others in this community, in the BPF world, spend countless hours just putting BPF print case statements here and there to just understand what was going on. And then some months ago at Elastic, basically we started working intensively and creating a lot of BPF programs for Linux security. And also, differently from other times in the past, I had like a lot of colleagues and a lot of people writing BPF programs. And so I needed a way to quickly understand the grasps in the code while, for example, reviewing pull requests or things like that, or just to understand the program. And so I sit down and I try to understand, okay, it's time. How can I do something that gives me information on line coverage of the BPF programs running in the kernel, even on regions of the code inside the BPF programs, or even on the branches, the code branches. For example, let's say that you have an if conditional with two conditions, and we want to be able to understand, even if the second part got short-circuited, so not evaluated at all, things like that. And how many times that if or a for cycle executed, things like that. I started with a strike, like experimenting various approaches for grabbing coverage from BPF programs. Like I remember spending, probably it was October or November, like 1 week trying to patch the BPF elf after I compiled it. But it was not a viable solution, because in that case I would have needed to keep track of the global state of the registers. I tried experimenting, inserting instructions, incrementing a counter in a BPF map, same as before. Nope, it's not a viable solution. And in the end, I reached out to the LLVM, and I started studying more intensively, more deeply the LLVM BPF target, which is just a bunch of LLVM passes. Basically, LLVM has this architecture that lets you that they use themselves, but lets you also write out of 3 LLVM passes to provide new functionalities to, for example, to the compiler or to the LLVM tooling infrastructure
So I guess let's just drill down a second on that idea of LLVM pass. Naively, I'm imagining that you've got some kind of object file. It goes through a pass. It's a slightly different object file, and then you can put that into another pass, and it will do some different processing to produce another object file. Is it something like that?
Yeah, basically, when for example we call clang -g -target BPF, but when we compile our BPF program, what happens is that the LLVM infrastructure executes a series of passes, or LLVM pass, doing things like BTF augmentation from the bug info, creating instructions to put in the BPF valve, and things like that. What basically you can do with an LLVM pass out of 3 LLVM pass, which is one part of the bpf-curve repository, is that you can, let's say, put yourself in the middle. You can tell Clang to do not output a BPF directory, but to output an intermediate representation that can be textual or binary. On that on that intermediate representation, you can execute with a tool that's called OPT. It's an LLVM tool, comes with LLVM. You can execute your pass and patch the intermediate representation. You can mess around with instructions. You can even annotate insert variables, annotate them with the bug info so that BTF will be generated. Things like that. You can have a lot of fun. You could, for example, write a pass for automatically converting the print key, the BPF print key things, or for inserting conventions. Like, let's say that you tag a map with a section map.leads, and all the maps tagged with the section map.leads, the pass will transform them in something else. I don't know, just something out of my mind, on top of my mind right now. And then basically with the LLC, which is another LLVM tool, you using as input the patch, the intermediate representation, you can compile it to the target ELF, the BPF1, and you can use it. And this is what basically that part of the bpf-curve repository does.
All right. So maybe we should take a look at, should we start looking at the repo? Would that be a good place to start? Yeah, let me bring up. There we go. So.
Okay, don't mind these leads directory is a test that I did before.
Now I'm curious.
But basically, the README contains instructions on how to build that. But as I was saying, basically this repository contains 2 main pieces: the LLVM pass, which is a library, lib-bpf-cov.so, that we need to compile, and then it contains a CLI, which is called bpf-cov, CCLI, that acts similarly to Trace. We will see later why it was needed to create and why I decided to create a CLI for this tool. So would
it be right to say that the library, the lib-bpf-curve, that's the LLVM pass, that's what's instrumenting your BPF code, your BPF program with the code coverage kind of instrumentation. Exactly. And then the CLI is what we're going to use later to look at the results.
With a difference. I let Clang, basically I did something, I let Clang instrument source-based code coverage, and then I transformed the things that LLVM put in the intermediate representation to something suitable for the BPF virtual machine, the kernel, to be run. Why is that? We need to do a step back probably on the concept of source-based code coverage, which is a kind of code coverage. It's probably the most precise one because it doesn't stop only to line level granularity, but gives you information also on branches, short circuits, regions of code, things that I mentioned before. Clang has these 2 flags one is -f coverage mapping, and the other is -f profile inst generate. If we go one sec before looking at the LLVM pass code in the example directory, and I open the make file that I did for the examples to help people try this out. Basically, you can see that I'm using these two flags here, these two Clang flags here, okay? And I'm emitting the textual representation of LLVM, intermediate representation of LLVM, textual one. Why these two flags? Because these two flags, instruments, they act. Also, them are implemented like LLVM pass inside LLVM. They instruments at the abstract syntax tree time. They understand your code and they understand where they have to put counters, incrementors, counter expressions, and things like that. Let's say that you have an if, a for, a function. LLVM knows because it contains the abstract syntax tree of your program that it will need to put a counter for the entering of the function, a counter for the entering of the if. If the if conditional contains branches, also counters for the branches, a counter for the for, and things like that. So I let LLVM and Clang do their work because they're better than me at doing that. And so then I patched the results, and we will see in a bit, for the BPF virtual machine in the kernel. So basically, if I open the source code of the source code of the LLVM pass, basically we can see, this is the main part. We don't need to look at all the other mess, but this is the main part. Basically, when since BPF is C code, let's say that BPF is a special breed of C code, okay? Source code coverage can be instrumented by Clang on C programs, even or C++ programs, things like that. But when it does, it injects in the intermediate representation things that the BPF virtual machine won't accept. No way. No, we want a set. For example, it inserts initialization functions like LLVM profile init, register other functions. If it's C++, even registers constructors, things that we can have in the BPF.
And we can't run those in BPF.
No way we can have something like that in the BPF virtual machine in the kernel. And then it also creates the counters, constant structs containing information about the functions that you're gonna get coverage for. Why there are two flags? I mentioned two flags. One is the coverage mapping flag, which basically encodes and compresses region, branches information in a representation we will see in a bit. And the other is -f profile instr generate, this one, which is basically tells LLVM to instruments your code for profiling. Okay, so these are something to do with profiling. Now, what basically this pass does, applies a bunch of modification to the LLVM intermediate representation, like deleting the initialization functions, the register function, all these functions that he created, because we can't have them. Fix the LLVM use of the variable, which is a variable keeping track of all the things that in the intermediate representation, all the things the program is using. Changes the sections, because the sections of the counters, the sections of the function names, the sections of the function data, things like that. Okay, but probably it's just it's better if I just start typing in the terminal here, and we can understand step by step. So let's say that we have this very dumb, unuseful BPF program. This one, sorry. Okay, it's a row trace point on C center. Good. Does nothing except telling you hello sometimes. But
wait a minute, there's a print K. Yeah,
yeah, I want to get coverage on the print case.
Okay.
It's meta.
Very meta.
Yeah, I just put a bunch, for here, 4 iterates a number of time. This is a variable that I'm gonna change from the loader to a number to see if we iterate that number of times. And if here, and this is the loader that loads this row trace point program, and which uses, let me, okay, open, we change the count to 10 because we want to iterate 10 times, okay? Then we load the program. And how do we execute them? How do we execute it? We execute it with BPF prog test run. This needs a parenthesis too. This needs some words. When I started looking at the coverage problem for BPF, I started thinking, okay, coverage is usually tied, related to testing, right? And so there's this BPF prog test run command of the BPF syscall, and I started investigating whether I could patch the instructions at this step, at this time, to let then the kernel run the patched instruction. Turns out that it was not a viable and very usable solution, and so I resorted to LLVM. But the problem is that I wanted something working with normal actual BPF programs and loaders. Something for that's because BPF prog test run doesn't support all the BPF program types that we have in the Linux kernel. For example, it doesn't support BPF LSM programs. Last time that I checked, at least it doesn't support.
Do you think it probably will in the future? It just doesn't yet.
It depends. It depends on the kind of program. There are issues, in my opinion, with synchronizations and things like that. That's probably that's a reason why not all the kind of BPF programs have the support for BPF prog test run. Also, the Fentry and Fexit BPF programs are not supported, for example. Since I needed something working on any kind of BPF program, I didn't want a partial solution. I wrote this tool that works nevertheless. I mean, whether you're just testing your BPF program or if you just are actually loading it and using it. And we will see in the other examples, for example, this one, the LSM one, this is a set of LSM programs that I just grabbed from the Linux kernel, okay? And I also copied their code from the kernel, from loading them, okay? And I'm not using here BPF prog test run. I mean, they are not using so, and this work we will see in a bit. So coming back at this dummy program, let's say that we want to compile it. I created a makefile that takes care of everything, because otherwise would have been too difficult even for me for understanding how to move things. So here in the example source directory, you can just write like with a prefix cov / name of the program and its loader, and it will take care of doing the steps that I mentioned before. Clang to LLVM intermediate representation, OPT with our bpf-cov LLVM pass, generating the BPF patched BPF-elf with LLC, okay? And then generating the skeletons for the loader with eBPF and all the other things that people working with BPF is used to do nowadays.
Okay.
I should probably, before compiling this, I should remember people watching that they need to compile the BPF, the LLVM, eBPF-cov pass. To do so, you can create the build directory in the root of the repository, and then you need to basically give configure CMake, and you need to tell it the prefix where your LLVM installation is. I tested this on an Arch Linux with LLVM 12. I bet there will be bugs on other distros, but welcome. Contributions are welcome.
Tool chains are quite difficult to install and manage, in my experience. So yeah.
Yeah, there are. So
and it's the one thing I miss about Go every time I'm doing BPF programming. You think, yeah, if it was Go, it would all just be the one thing.
And so basically, we compiled we obtained this library here, eBPF-cov.so, this one, that's going to be used in the makefile here in the examples. For example, this is the makefile that we were looking at before. We are instrumenting for source-based code coverage, okay? Then we are using this output to execute eBPF-cov, so okay? And then we're compiling it to the actual BPF alpha object that we are going to load with our loader. So now that we build the pass, the LLVM pass, we can just calendars events. I did them. Okay, compiled. Before running it, before going there, let's take a look at the output directory here. .output directory. There's this cov directory where basically I kept all the intermediate files, also for explaining to people, for making it simpler to understand what it does. So here, this one, don't get scared, it's a bunch of text, but this is the intermediate representation that I obtained from Clang. Okay? So let's take a deep brief and let's take a look at it. As you can see, I have things like this one, covrec and an hash, okay, containing a bunch of encoded code coverage regions and things like that, okay? I have this LLVM coverage mapping struct. It's constant, but it's a struct containing things like the format version of the coverage, the names of the functions being targeted, and things like that. I also have the profiling runtime, things that I can't have in the BPF virtual machine, as I was saying, this one. And then I have this prof-C and prof-D. Why I have two prof-C and two prof-D? Okay, let me explain this. If we take a step back to the source code, we can see that there's BPF program here, and then the actual function, our BPF, that implements our BPF row trace point program. So why we have two BPF prof-C? Prof-C, C stands for counters. Because BPF prog creates a function, okay? And so LLVM knows that it needs to put a counter at the enter of the function generated by BPF prog, okay? Then it puts another counter here, another here, and another here in the for. And we can see this in the actual intermediate representation of LLVM. For example, look at the dimension. 1. This is the counter for BPF prog, the function generated by BPF prog macro. Okay. This is the counter for our actual BPF program. 3 counters: the entry of the function, if, and the for. If it's too little, I can probably zoom. It's better now.
Yeah, it looks quite a lot smaller for me than I think it does everyone at home, just because of the way I've set up my screen.
So, and there's a section here, an help section here that we'll talk in a minute. Prof-D is just a global struct representing information about the function being targeted for coverage or for profiling. This also works for profiling. And it contains things like an ID of the name of the function, another hash obtained from the complexity of the function, points to the counters relating to that function, and things like that. Okay, this is a struct, basically 48 bytes. There are 7 fields. If we count it, these are 48 bytes. Then there are other things like profile init. In fact, if we go here, you can see that Clang put in our intermediate representation things that we can't have in the BPF. Like this.
That's one of the things that you're going to delete in the next pass, right?
Yeah. In fact, if we open the bpf.cov.ll file, which is still, it's basically the output of the OPT with our pass on the previous file, we can see that basically what I did here, I transformed the structs and the field of the structs into single globals. For example, keeping only the things that I needed for later. For example, I removed the coverage mappings, and I'm going to explain in 10 minutes why. Then I transformed the LLVM coverage mapping struct fields in 2 constants, okay? And I changed their section to custom BPF elf section. Why is this? This because I need later to recover this data, to dump this data from a continuous section of the memory into a format, into a file that respects a format. That's called prof-row, which is what LLVM uses for code coverage, for source-based code coverage. When you instrument source-based code coverage on a normal C program, basically it puts all that mess inside the intermediate representation and compiles the ELF. And when you run it, your instrumented C binary, okay, basically automatically at the exit, because of the constructor of the init, it understands to flash out a prof-row format. The prof-row format, we'll see an image in a bit maybe, contains information that we need, like the counters, the functions that we're targeting, things like that. To continue, what I did, so basically I created my prof C here, okay, changing the visibility, the linking to make it working for the BPF virtual machine. I flatten the prof D structs into 7 fields because I need them in the. I did the same for the other prof C variable and for the other prof D variable. Okay, now a word on why this is, my opinion, cool. Let's take a look. Let's come back to the previous unpatched intermediate representation, and let's take a look at the functions, at the function itself. This is our UX6 center, okay? This is the BPF function. If we take a look here, we can see that prof C, this is prof C, okay, is getting incremented automatically, like add 1 here, add 1, okay. So when I saw this, I was like very happy, because the alternative that I had in mind initially was to use BPF maps to update and increment the counters, counting the lines or the counter expression, things like that. And turned out that if you look at the intermediate representation of a program doing a lookup in a BPF map, then incrementing the value and sending it back, it's a lot more instructions, and because there's the call to the helper, and there are arguments. Helpers, BPF helpers for updating, for using maps have arguments. And when you have arguments, it means that you need to take care of the global state of the registers. You need to move R6 into R1 and then shift it back, things like that. And I didn't want to complicate things so much. I mean, I guess it's just a bit complicated. So I wanted to keep it as much simple as possible. Anyway, you can see here, we are incrementing.
I guess it might actually, if you'd had those kind of inserting those helper functions, it could have significantly changed the code that you're trying to instrument.
Significantly changed the code, the register, and the things. And the paramount aspect is that I'm not changing the instruction of the functions this way. I'm not touching. I'm just changing the globals here, the constants and things like that. I'm not changing, because this works in a BPF if your kernel supports BPF global data, okay? So if you have something like this in your normal BPF programs and your kernel supports it, it's basically what I'm doing. It's like if I was creating here prof C const volatile int prof C, etc., 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 etc. It's just that I'm letting Clang do it, because then Clang and LLVM knows where to put the increments here, here, and here. Otherwise, I couldn't understand on my own. So now we have this, and we have all the objects here. You may notice here, Chris, that we have .o and .obj. These are two BPF helps. One, it's the one obtained from the patched intermediate representation. That's fine, can be loaded. The other not. But why is that? Because the other contain the coverage mappings, the coverage mappings. Do you remember that encoding lab 128 encoding that I highlighted before? These variables here Okay, these variables here, all these numbers, if you decode them, basically this contains region from line X column Y to line X plus 3 column 3, things like that, all the mappings, the branches, all this information.
So you can tell what that relates to in your source code, in your
yeah,
file.
but I don't know, I don't need this, because basically I only need this in the object file that I'm gonna give to LLVM COV tool, which is the one that generates the coverage, because that tool reads the ELF, understands that basically this ID corresponds to this function, this one, look at the same, okay? And then basically knows that the counter that he has relates to a particular part of this encoded. I don't need it I don't need to load this in the kernel. We don't need it.
Makes sense. Yeah,
it's just constant data that's there that represents. In some
you
way,
only need it at the point where you're showing the results.
Yep. So let's close this mess, because I don't want to scare people. I can feel. But okay,
maybe since we mentioned there are people out there, let's just quickly say hello to a few people who've been watching. So hi to Mattia, hi to Siam, here's a familiar face, Lorenzo, hi, and also Yarin likes your accent, Leo.
Thank you, Yarin. I can do nothing about that. I can patch it. I can't.
All right. So would it make sense now to actually look at some program and some code coverage being measured on it?
Okay. I created a CLI, as I mentioned before, because we can't just hook the exit of a BPF program from the Linux kernel like normal C instrumented program do, because I stripped those functions, and even we could it. Even if we could have done that, it doesn't sound to me a very cool thing to do, a very nice thing to do. I could have patched the loader, but that would imply creating another library that people needs to link with their loader, but people can use eBPF to load the BPF.
Yeah,
but
there's loads of different loaders. Yeah,
other people can just use ELF tool chains and parse their ELF and load the program the way they want. So it didn't sound reasonable to me. And so I created CLI. What the CLI does, the CLI basically, it's like, imagine, think of it like trace, okay? You call it, we will see in a bit, and you give your BPF loader binary that loads your BPF program, and basically traces it, understands and finds all the things that we patched, in particular the BPF globals with their section. In fact, I forgot to tell you, look, I changed the sections here, like raw data, prof D, data, prof C. The difference is that this is constant and the counters are not constant. And understands this section and pins them to the BPF file system as BPF maps. Okay. This way, when the execution completed, either because it just ended or you stopped the CLI, we will have data in the BPF pinned maps. And with another CLI subcommand, we will generate the prof row from those maps. And then the prof row will be perfectly in line with the LLVM format, which, by the way, was documented nowhere, and I had to reverse engineering it. And I wrote about a nice post on my blog about this because it was a mess. But now it's more clear. So let's just sudo run it. Okay, let's run the binary that we obtained. Okay, we have this thing in the COV directory. Okay, let's run it. Okay, let's observe one sec here. It found raw data COV map, dot data dot prof c dot raw data, all these custom BPF sections. Okay, and they pinned them to the BPF file system in this path COV name of the program, prof.d. So this means that if we now just use fantastic BPF tool by Quentin, thank you, Quentin, we can see we have raw data gov map, data prof c, raw data prof d, prof n. Okay. Let me see if sudo BPF tool dump map dump. Yeah, let's do this. I don't remember. Oop, I don't remember then. Okay, let's see the counters. Okay, prof c is the count, so ID 92. Okay, this one.
Okay.
92. Oh, so we know
Very
that
cool.
the BPF prog macro entered one time. The function generated by the macro entered one time, which is the same the function that we basically see in the source code. The if never executed, and the for executed 9 times. Why is that? It's correct. It is. Let's see. Let me see. Let me show this to you. Okay. So
yeah,
we
count was 10, wasn't it? Yeah.
10, and so 1 to 10, 9 executions. Correct. Why this doesn't evaluate? Because if I go look at the test run thing here, basically I told it and connect. Okay. And so basically that doesn't evaluate. We can change this program if you want live. Like let's just think about demo gods. Demo
Okay.
gods. And like it works.
Let's
So
do it.
1 second. Let's complete this, and then
Okay.
basically now I can sudo bpf-curve generate the prof row. Okay, it's basically like this. Okay. So there's this command, this flag to tell to the CLI, hey, unpin the maps that you just pinned before, clean things. And okay, we have a prof row file here, which is a binary file. But if we take a look at it, we can observe something very cool. Okay, these bytes here are the either. What in the LLVM format is called either, and it contains things like the number of function being targeted, okay, the version of the format, the total number of counters, so 2 function, 4 counters, 1 plus 3 if we remember the version, things like that. This is always 1 for reasons I will not expand here. Then we have these 48 bytes, which is basically the prof distract that we mentioned before. Let's remember. I stripped. Usually in the prof row format, it contains like the address of the function. I stripped that also because I didn't want to expose, and that it didn't sound correct me to expose the address, the kernel address of the function. This is.
Yes.
And so basically, this is the idea of the function. This is the number of counters that this is the function generated by the macro. Okay, this one. And this is our actual function, which has 3 counters. Okay, and starts at offset 8 in the following section. So basically, what this is telling me, 0. Look, under the ID here, I have like an offset. Okay, this 8 here means that this section, which is the prof c section, this is the .data.prof c elf section in memory, dumped to the prof row file. So this is 1, which was the first value in that we saw with BPF tool before. Then we have 1, 0, 9.
Oh yeah, yeah.
Exactly like that. So 1, 1, 0, 9. Total 4 counter. 8. This is the offset. So this function counters starts here after 8 bytes of the initial of the init of the counter section. The last part of the prof row format, it's a padded section containing the names. It's encoded and compressed. It contains the names. Nothing really cool to take a look here. So now let's say that now we should be able we can use LLVM prof data. We can do two things. We can use LLVM existing tools because the prof file is compatible and generate things, or we can use basically another CLI subcommand that I created called out that gives you the coverage. So if let's do that, because I don't remember all the flags of LLVM prof data. So I created this opinionated out thing. Okay, this one. But let me remove things that we don't need for now. So bpf-curve, bpf-curve verbosity, output in the leads directory, and we give it the prof file. Okay, the prof that we just took a look at. I did something wrong because no, it should be this one. Let's after the out. So bpf-curve out. Okay, it should have worked. So if we go to the leads directory, now we have a wonderful HTML
file
report that I need to change to share the other screen. Let me see if I can do it. Let me see how to change the screen here.
There's an HTML viewer that you can build into, a plugin for VS Code. VS Code does everything.
There is. I should install.
While you're looking for that, I'm just going to show Quentin's comment because he appreciated you mentioning him in the context of BPF tool, but he also wanted to mention Jacob Kaczynski and many others who.
Yes, I know. So sorry for people that I didn't mention, but thank you all anyways for that tool. It's very cool.
I think Quentin has also done a lot of work on that as well. So
let me see if I can stop the screen and share the other. Share screen, window, and this one. Can you see it?
There it is. Yeah.
It's wonderful HTML report. The opinionated CLI command that I created also support textual, so standard out representation or JSON or others. I don't care. I like HTML without JavaScript. So as you can see, we got information about function coverage, line coverage, region coverage, and branch coverage. If we enter it, we can see what we understood by looking at the pinned map. So that basically this if conditional never got executed, 0 line here. Okay, because basically the if was false, and it was
that branch annotation is the
branch annotation. Here in the for we can see that basically the last index was 9. In fact, it got executed, the condition of the for got executed 9 times true and 1 times false. In fact, so yeah, this works. But if we come back to the code now, to VS Code, I can show more complicated things. I can, for example, I would like to show people how to use it for BPF LSM programs or for Fentry and Fexit programs, and then we will back at this visual HTML fancy visualization. So let me.
Yeah, let's do it. I'm going to show Alex's comment. This is excellent. I entirely agree. Thank you, Alex.
Okay, sure. Can you see my screen?
There it is. Yeah, we're back in VS Code.
I became a pro at live streams. Thank you, Litz. So let's take a look at the other programs, the other example programs. I copied this LSM BPF, a bunch of LSM BPF programs from BPF self-test in the Linux kernel. Okay, there's LSM file protect, a sleepable LSM even here. All these programs don't support. You can't use BPF prog test run for this. So So in fact, the loader of the tests in the kernel, of the self-tests in the kernel, just load them and then asserts things on variables, okay, on values contained by variables. I just copied it, and then we can basically compile it. Let's come back to the example source directory, make cov lsm. Okay, since we are here, let's do the same also for this other example, Fentry. Basically, it traces the enter and the exit of the do and link at. Okay, and the difference is that also Fentry and Fexit programs are not supported from BPF Prog Test Run. Last time that I checked, the difference is that this loader it keeps going, and we will stop it by hand. So will give us time to create to unlink some files and then to get with BPF. Okay, so let's compile these two. Make cov Fentry. Good. Let's resort to our CLI sudo bpf-curve verbose to run. Let's run the LSM. Okay. Things. Let's run the Fentry binary that we obtained. As you can see, this keep going. Let me go the attach leads and touch unlink leads touch Lisa in Italian unlink Lisa. Okay, let's go back here and stop this. Okay, good. Sudo bpf tool map show. As you can see, we have 1, 2, 3, 4 for the LSM, 1, 2, 3, 4 pinned map, eBPF maps for the Fentry, because it's like 4. We have like 4 bunch of information, either data counter names. So I pinned these maps, and now let's generate the prof row file from these maps. Sudo bpf-curve gen, this one. Okay, good. We obtained the Fentry prof row in this path. Let's do for LSM. Continue the maps too. Okay, LSM. Good. Now let's the cool thing is about the opinionated out command, which is the simpler one that I created, but the cool thing is that it basically can take in more prof rows coming from different BPF programs and show the coverage for all of them.
Okay.
So basically, out, BPF out. Yeah, this one. Yes, bpf-curve, very verbose, out, format HTML, leads, Fentry prof row, and row enter prof row, LSM prof row. Okay. I need to switch screen again, but we can already see here leads that we got Fentry BPF CHTML, LSM, so the three programs that we want coverage for. Let me change the screen. Share screen.
While we're changing screens, I'm going to say hi to YMO, who I missed earlier. Hello, nice to see you again. Okay, I can add.
No, this is wrong.
That is wrong.
And let me see, window. Where are you? Where are you? Okay, I found it.
Okay.
Sorry.
There we go. That looks more like it. Yeah.
Okay. Let me. Okay.
So that's the index file from that directory.
Yep. The index file now got also Fentry and LSM programs that the loaders of these programs doesn't use BPF Prog Test Run, so bpf-com works nevertheless. Either you're testing your BPF programs or just using them, loading them. Look, these basically the dual link cut executed 8 times. When I created Lisa leads and I linked them, and then when I gave enter on my shell creates files that got tracked. This is what really we can see something really more interesting.
Okay, now we start to see the branch. Yeah, okay.
These are the LSM programs. Okay,
Yeah.
for example, the file and protect. And let me see if I can zoom. Okay, if we take a look here, look this. For example, this if conditional. Okay, it got tested 10 times. Sorry, 10 times, and it detected 2 branches, first branch and the other branch.
Yeah.
It even tells us that since the first branch is stack variable was false 8 times, monitored PID never got executed in those cases because it got short-circuited.
Yeah. Okay.
So basically, and it was true 2 times. In fact, the increment of mprotect count actually happened 2 times only, and it also works on inline conditions like this. And I think that's it. I mean, I think that even with more
Yeah.
conditional.
That's very cool. So seeing that, and sometimes it's very difficult to create a test case,
Yep.
that will take you through all the different possible branches. Maybe you're relying on something failing that never fails. Would it be possible to do some kind of fault injection? I mean, not today, but do you think you could use the same kind of process of
an LLVM pass to
yeah
to do what? To do the tests?
to inject faults, to say, so for example, if something that never fails to change the outcome of a test.
Yeah, it's possible.
Yeah.
It's possible. Definitely.
Yeah. Because I remember that from
can also be used
years ago. Like,
yeah. The same approach can also be used also at loader time, because I'm patching the BPF program, okay?
Yeah.
But also the loader gets compiled with LLVM infrastructure. So we could write passes that automatically do things, but I mean, do things like eBPF does, patching instruction, fixing up instruction, things like that. It's a very nice approach because while doing it, I learned a bunch of things. For example, I learned how to annotate the counters, the variables that I was creating, and in the initial section of the LLVM intermediate representation for having then BTF working. I didn't know that, so I was very happy to learn that this new thing.
Yeah, I've definitely learned something about these intermediate representations today, so that's been really helpful. Yeah.
Yep.
Yeah. We got some nice comments here. Oops, clicked the wrong thing. So first of all, hello to Sadiq. Thank you for joining us. YMO says this is super cool but complicated. But I think the output here is pretty easy to read. It's pretty clear to see what you have or haven't covered, and that's really the main point.
It's complicated, but it's something that, I mean, in reality, it all resorts to, once you have the bpf-curve library, the pass, to change your usual flow of compiling BPF programs by injecting the OPT step. But usually you have clang target BPF. You need to add those 2 flags, -f coverage mapping and -f profile instr generate. And then you need to basically tell the make file, whatever the CMake, whatever you're using, to emit the intermediate representation rather than directly the ELF. On that direct intermediation, you're gonna use the pass, and then you piping to LLC, you can get your ELF. Once you have that, the rest is it's like all the other times. It doesn't change, because then you're gonna generate with BPF tool the skeletons. Then we can take a look at the skeletons too, if we have another 2 minutes, let's, and if you want.
Yeah. But before we do that, let's just so Yaron's made this very good point about integrating this into your I guess CI pipeline, and maybe creating coverage reports. I mean, I think staging in Kibana would be just one possibility for doing that, but I think that's probably very, very true, right?
Yeah, how this can be integrated into pipeline and Elastic to create some pipeline coverage reports for staging in Kibana. That's too far, but but yes, it can be done. I started to integrating it in what we have at Elastic, but only on the build side. So changing, for example, the CMakes that we are using for compiling the BPF programs, giving them a flag, an option to instruct them to just generate the coverage, the patched programs for coverage. And once you have that, then your loader, if maybe it's important to highlight, Leeds, that I'm not changing the loader.
Yeah, I like that. Yeah.
I'm not changing the loader, and then that's a very good thing, because otherwise would have been really complicated. I'm just changing and patching the BPF half, okay? And so if you don't need to rewrite your loader, it will continue loading it just with with some counters hidden in it, and so the rest of the flow in the pipelines, it's always the same.
Yeah. Here's an interesting question. Could you do this with Rust?
Yes.
My gut feeling is if you could get the intermediate output from the...
Yeah, you can. The way that Rust coverage is implemented is like this.
Yeah.
Basically, they use LLVM infrastructure with Rust SDK to basically instrument Rust programs, and then obtain the coverage. Very, very similar to this approach. It's just that they do this in the Rust compiler.
So maybe that's a challenge for someone out there who's writing their BPF code in Rust to bpf-curve on it and report back and tell us how it goes. We've just got a couple of minutes before we're at the top of the hour. I know you just mentioned looking at the skeleton code. I don't know if that's something we can do very quickly.
Yeah, very quickly. Yeah. Very quickly. Output. Okay. Cov. Let's okay, this one.
And is this similar to the skeleton you would just get from similar to or even the same as BPF tool gen skeleton?
Yeah, basically when the makefile data root compiles, it understands by looking at eBPF understands by looking at the alpha that there are other things like this, okay, and creates everything, but doesn't the skeleton? I don't patch it. I mean, it's always the same. The loader knows nothing about it. So.
Yeah. Brilliant. Well, yeah, I think this has been really interesting and really helpful. There's another nice comment. So first of all, thank you very much to everyone who's joined us from around the world. I hope you found this interesting, and let us know how you get on if you have a go at measuring your code coverage. We'd love to hear about that. And if you want to find the links to using BPF-curve, you'll find the links in the show notes. Those blog posts, they're blogs by you, is that right, Leo?
Yeah. The first explains basically all that we have said during this live stream, but in words, in text. And the second one is like a deep dive, demystifying the LLVM prof row format, which was paramount to this operation.
Great.
And the third is the slides of my tool, FOSDEM LLVM track about this tool. An option factlets will be, and the LLVM maintainers asked me to do so, but I don't know if I have time and will to contribute this directly to the BPF target in LLVM, so that we just expose it with a flag, like when you compile -bpf-curve.
Right.
In LLVM,
Yeah. That sounds like a make it easier as part of the workflow. Wonderful. So thank you very much for joining us on that today. One thing I will mention is for the audience, we have just this week started publishing a newsletter, an eCHO newsletter. So I will put the link into the show notes for signing up for that. You may have already received a copy of that if you, for example, joined us at eBPF Summit. We've only signed you up for the first instance of that newsletter. So you do need to sign up if you want to keep receiving it. But it's basically going to be along the same lines of what we cover in these live streams, news from around the community, news about eBPF, news about Cilium, and we hope you'll find that interesting. We have also got an eCHO news channel now on Slack. So within the eBPF and Cilium Slack, you'll find eCHO news. That's a great place to let us know about things that you've been seeing and finding exciting around the world of eBPF. So with that, and we've just gone past the end of the hour, I'll say thank you once again to Leo for joining me today.
Thank you for having me.
I hope everyone stays well and stays safe. Bye now.
Bye.